Hey guys, this is Mohammed Zuhair from COPS IITBHU CSE second year. Today I'll be discussing the basic concepts of Disjoint Set Union, also known as DSU. So first, let's see what DSU is. It's a unionizing data structure which unionizes a set of data into specific set. Like, yeah, let's take for example, we have a certain we have certain disjoint sets. Let's say we have one, two, and three, four. Let's say these two are in one set, one, two are in different set. Well, like one is in a different set, two is in a different set, right? So we will say that uh, one, two, and three, four are disjoint sets, right? Because they have no intersection. So now, for union, like let's say that now it says like one is inserted in this set, right? So what will happen is one will be inserted in this set, and one will, as a whole, like one will be here in this set, and we will not consider one to be alone, right? It will not be like it will be in this disjoint set. It will be in 1, 3, 4, right? So this is the this is the what we do. Like this data structure provides the following capabilities. Let's say we have given several elements, each of which is a separate state. Let's say initially, sorry. Let's say initially one, two, three, four. Everyone is disjoint, right? None is connected to none. Five. Now what happens is, let's say they say that one and one is in a set with two. What we do is we can unionize one and two, like then we can unionize 3 and 5, like something like that. So what it does is it unionizes certain disjoint sets into a set, right? So let's DSU will have an operation to combine any two sets, and it will be able to tell which set a specific element is. In which set a specific element is. The classical version introduces a third operation and get a set from any element. Okay, so we'll be discussing the basic thing, right? So what this basic thing is, we will be just finding out which of these elements is in which set, and how can we unionize these sets, right? This is all we will be learning, like the basic functions which we'll be using, and we'll be learning about today is, first one is make set. What make set does is it creates a uh, uh, disjoint set, like 2, 3, 4. These all are disjoint sets as of now. So make set 1 will create this, make set 2 will create this, make set 3 will create this, make set 4 will create this. Union set, I'll discuss how they do. Like first of all, let's see what these does. So yeah, so union sets AB does is, let's say we are given union of sets. I am writing small form, union of S. Let's say 1 and 5. So what we need to do is we have to unionize 1 and 5, and this is the thing, right? Like if after unionizing, we know that these two are now in the same set, we'll be considering this in the same set, right? So yeah, union underscore sets unionizes A and B, like makes A and B like unions. Not only A and B actually. Like let's say A1 is connected to some 7, right? So what happens is the whole thing will be unionized. Like you're understanding, right? The 1, 5, and 7 whole thing will be unionized, because 1 and 7 is already unionized. So these are like, if 1 and 5 are created, we have to also take 1 and 7, obviously, because the name is disjoint set union, right? And find set, what find set does is, now what we do in the process, like let's say that we are unionizing 1, 7, and 5. So what we do is we give this set a certain ID, right? A certain ID which we will be like taking to identify this set, and this ID will be the value of any of this 1, 7, or 5. which we'll be learning, which one will be when we will be learning after some time. But any of these values we can take as the id of this set. Let's say we are taking 1, so this means that the like this value 1 represents this whole set. Like if we say that in which set 7 is, it will say 1. So if we give find underscore set 7, it will output 1. If we are denoting it by id 1, if we are denoting it by id 5, then find underscore set 7 will give us 5. So a one set can be represented only by a single id. We will be doing this thing. We will be representing an id, an disjoint set using an id, right, to identify every value which are in this set. So the most basic and the naive approach which we can think of is, let's yeah, the naive implementation. Make set, like we'll be creating a parent. Let's say 1 is here, 2 is here, 3 is here, like let's say, yeah. So what makes it does is it creates, like it initializes parent of v equal to v. What does this mean? Parent of 1 is 1, which means the set in which 1 is, the set which 1 is denoting is 1 for as of now. The set which 2 is denoting is 2 as of now. The set which 3 is denoting has id 3 as of now, right? Find set, what find set does, it finds the, like it finds which value, what is the value, what is the id of that value in the set, right? It gives us the, so what we do is, if v equal to parent v, let's say that we are given like something like this 7 and 6, all of these are connected, right? So these are in one set, 1 7 and 6, right? And now let's say that the parent of this whole, or the id, if we say like the parent or the id, same thing, of this whole set is 1. So let's say that uh, this the this whole set will be like if we do find set of 7, we will be getting 1. If we do find set of 6, we will be getting 1. So how this works is, what we do, we initially we have find, we send 6, right? Let's say we are sending 6 and we need to check which it which set it belongs to, right? So if v equal to parent v, that is if 6 equal to parent 6, like the id is 6 already, then we know that it is already in that, like we don't need to check any more stuff. It we will know that it is in that, in this set, like the id will be that only, right? Yeah. After that, if we don't find it, what we do is we will just, like if parent is 7, we'll be just send, like actually parent is 1. In this case the id of this whole set is 1, so we'll be sending find set of parent 6, right? Find set of parent 6, find set will then like we will be sending find set of 1, right? If we send find set of 1, what we can see is 1 is parent of 1, right? So we will, like we can easily say uh, that we have the set of this 6 to be 1, right? The set id of 6 is 1. Similarly, if you take for 7, you can get something like that only. You're getting, yeah, this is find set. And union sets, union of set is done something like this. Let's say we have 176 and we need to unionize 1 and 3. We are given union set 1 and 3, like I'm not writing, right? So what we need to do is we need to unionize 1 and 3. So either parent parent of parent of 1 will be equal to 3, right? Or parent of 3 will be equal to 1. After connecting, imagine after connecting, either one of these will be true, right? Cause it is simple, because this has an id of 1, this has an id of 3. So if we are, if we shift this to this, like we are saying, like as I said earlier, that this parent thing is kind of dependent according to how you want the parents to be. If you want the parent of 1 to be 3, then you can say that this is a parent of, like 1 as a parent of 3, and hence this will also have a parent of 3, and now the whole set will have parent 3. If you want parent of 3 equal to 1, that simply means that yeah, so 3 is connected to 1 because they have the same parent, right? If a set has same id, we know that it is in the same set, right? So that's the thing, this is done here. So now there is this thing called the path compression, right? Let's discuss about the path compression. Yeah, so let's say we have something like this: 1, 2. Let's say we have a tree, kind of tree thing, and we have something like this: 6, 4, 5, right? Let's say we have something like this connected, and we know that parent of, we are saying parent of 1 is 1, parent of 2 is 1, parent of 4 is 2. As of now, the immediate one is their parent. Okay, parent of 5 is 3, parent of 3 is 2, and parent of 6 is 3, right? Now what we do, this is the, like the most basic, the connected, the just connected person is their parent, right? This is the easiest, and like, yeah. Now what we can say is, let's say we need to find out the parent of 6. What we do is, like in the naive approach, what we were doing is, we were just find set parent, and like we were just going through all the depth and then setting, like, and then sending certain value to the parent. In this case, what we are doing is, in this case, we are giving parent v equal to find underscore set of parent v, like let's say 6, like, yeah. So 6, parent of 6 is not equal to 6, right? So this condition is not true as of now. So we go here, parent of 6 equal to find set of parent of 6, right? So it pushes off to this parent of 6. Okay, parent of 6, I'm writing a denoting L by p. So parent, like, it sends, it's recursively calls parent, find parent of 3, right? Obviously you can see, find set of 3, because it is just immediate. Now what it does, 3 goes to 2, parent of 3, recursively calls 2, and parent, like the 2 recursively calls 1, and what we get finally is, we see that p1 and p1 are equal, so we return v, which is 1, right? So all the values are in this path are set to, are set it to 1. So we can see that this graph is looks will be looking something like this: 1, as everyone's parent is 1 now, in the path from 1 to 6, this graph will be looking something like this, right? So this is something known as the path compression. And after, like, doing this path compression, the average call for every average call per query uh, turns out to be o log n. You can search about this, like the reason why this is o log n, or you can just ponder upon it a bit. This can be a exercise to you, why this is called o log n, right? Like why this is o log n, on average per query, right? Now, as I said, that unionizing, we are using union sets. Now union set can be, like, there are many possibilities of unionizing, like as I said, that if we are unionizing 1 and 3, right? So we can make parent of 1 3, or we can make parent of 3 1, isn't it? Both of these are possible. So that's the thing. So that is what we are discussing about. Okay, yeah. So there are two types of union we will be discussing as of now. One is size and one is by rank, right? So by size is something like, A person with more size, like let's say 1, 6, and 7 is here, and we want to unionize it with 3. So it says that if this has a greater size, right? If this has a greater size than this, then this will be given the parent value, like the parent of 3 will be 1, like the heavier part will always turn out to be the parent. This is what heavier in terms of the number of elements, right? So this is what it like wants to say. And like you can see the code, if like a equal to find set a, b equal to find set b, if a not equal to b, we know that if a equal to b, then both are in same set. It doesn't make sense to unionize them, right? If size of a less than size of b, we are swapping, and then parent of b equal to a, right? And then parent of like size of a plus equal to size of b, and like we are adding a size to here. This is one thing. And this rank, this is a concept which we can use in depth of trees, kind of. Let's say that we have tree depth 1, 2, 3, 4, something like this, 5. So it says that a person with more rank, like the you can see that if rank b is greater than rank a, will be swapping b and a, and the now value with more rank will be given the parent, like the value with greater depth, like something like that. You can easily guess it. Like both are really similar codes. You can easily understand what this wants to say. Right now, there's this thing. After using this union by size or rank, and after using this path compression, you will be getting this complexity to be O of alpha n. You can search about this, is called the inverse Ackermann function. Inverse Ackermann function. Ackermann function. So you can learn about this function by yourself out of your curiosity. It doesn't, like, we don't need this thing like how this alpha works or something like that. We don't need an CP, so I'll not be discussing about that here. Moreover, this alpha, what I can say about this alpha is like approximately alpha n, for n to be really huge, let's say 10 to the power 100. Also it tends to be like this is a constant operation. We can say that O of alpha n is a constant operation, kind of O1, right? So this is a really like really great improvement. And it costs alpha n, and you can read about how this works and this Ackermann function by yourself. Yeah, so this is all about disjoint set union. What we do is we unionize sets, and we do some path compressions, and that's it. That's what we do in unionizing sets. So yeah, yeah, there are some practice questions which you can, one second, just yeah. So what I was discussing was, let's discuss this, the one of the questions. Code forces round 25. I don't know the round. Contest code 25. Question D. I'll be discussing, like, let's read the question first. Says that roads not only in Berland, right? So it says Berland government decided to improve relations with neighboring countries. Cool. First of all, it was decided to build new roads so that from each city of Berlin and neighboring countries, it became possible to reach all the others. There are, sorry, there are n cities in Berlin and neighboring countries with exactly n minus one two-way roads. Cool. Because of the recent financial crisis, the Berlin government is strongly pressed for the money. So to build a new road, it has to close some of the existing ones. Every day, it is impossible to close one existing road and immediately build a new one. Your task is to determine how many days it would need to rebuild the roads so that from each city it became possible to reach all the others, and draw a plan. Like, yeah. So the question says, what the question says is, we have n cities connected. We have n cities connected by n minus one roads, right? Roads. Sorry. And it says, we are in cities, and it says that there are we need to create roads such that everyone is connected. We know that using n minus one roads we can connect everyone. It is like obvious thing, right? So it asks us to what is the minimum number of days we need to do this stuff. If we can do one at a day, and what we can do is we can remove one road at a day and add one immediately. This is what they ask. So, yeah, let's take an example. Let's say we are taking 1, 2, 2, 3, 3, 1, 4, 5, 5, 6, 6, 7. Okay, cool. So, let's say we have 1, 2, 2, 3, 3, 1, 4, 5, 6, 7. Right? This is it. So it asks us to we know that if we cut any of this, we know that we can uh, like reach n minus one cities using, we can use n minus one roads to reach n cities easily. Like a connected uh, like a tree can be easy, like a tree is made using n minus one edges, so everyone will be connected in n minus one edges. So we know that if everyone is not connected in using n minus one edges also, we are sure that there will be certain cycles, right? We know that there might be a cycle. So it's kind of like the this there is a cycle. So if we cut any of these edges of this cycle, let's say we cut this and we join this, or we cut this and we join this, we know that in one day we can do this, and that's it, everyone is connected now. So we know that. So the main thing what we have to do is, we need to see which of these has a, like which of the connected components have a cycle, and we need to cut that cycle part and we need to join it with some other part which are not connected. This is the basic thing which we need. This is the basic thing we need to do as of now. So yeah, so let's discuss about, let's discuss the code. Yeah. So I have used parent 1020 because there is 1000, the constraint is 1000. So you can use naive approach also, I guess. Yeah. Now let's this is the make set, this is the find set, this is the union set. That's it. I have not used any kind of union. Like, that's why, I solved this question pretty early, I guess. So by that time I guess I didn't knew union by rank and by size. So what I did was I uh, uh, the number which is lower was joined to something like that. What is what I did. Like if b is greater than b is connected to a, something like that is what I did, which is pretty that's why I had faced certain problems over here, which you can easily overcome using union size. But yeah, I insist that you write your own code and don't use this. You use union by size and something like that. Yeah. So this is my really old code when I was solving this problem approximately a year ago. So yeah. So what we do is, there is this n, we have n cities, and then we take and then we create every city, which is like every city is disjoint as of now, right? Now what we do, we have n minus one roads, so we join, and we can, like, a and b are joining those. So what we do, we just we just unionize union ab. Like, the thing here which I'll like to say is, when do you know there is a cycle? Let's say 1, 2, and 2, 3 is connected. Now there is a edge between 1 and 3. So if we check parent of 1, let's say parent like the id is 2, let's say, right? The id of this whole this thing is 2, and we know that parent of 3 is also 2, right? Sorry, parent of 3 is also 2, right? So we know that both of them has the same parent. If both of them have the same parent and still there is a edge, we surely know that it's a cycle, right? Because they are already connected and we are connecting them again, so it's obviously kind of cycle. Yeah, right. So this is the thing. Yeah. So if both of them are equal, what am I doing is I am finding the set z equal to find set a, z b equal to find set b, and I am inputting v dot pb equal to make pair ab, and then, and if it's they are not same, if they are not same, obviously I'll be unionizing them, obviously, right? So I've unionized them. Now I was using union set z comma z1 again here due to my uh, weak this thing, right? After using this, I again had to do this because of this weak union set function. Never mind. We know that the number of cycles is equal to the answer, our answer, right? Like the number of edges which will form a cycle is equal to our answer, because total there is n minus 1 edges, and those cycle, we don't want the cyclic edges, right? So we will be cutting them. So yeah, so if v dot empty, we are outputting 0, else v dot vs. This is also, yeah, this is kind of size, like my v dot size, you can also write v dot size. That's the thing. Now what I am doing is I am using a set to denote the parent of every element, like kind of something like this. Yeah. So I am storing all the parents which are distinct till now, which means, which means that they are not connected. The parent of 1, 2 and 3 is 1. The parent of 4, 5, 6 is, let's say, 4. So we have two parents which are still not connected, right? So this is what I was trying to do over there, storing it in S. Then I stored it in a vector so that I can use indexing over it, and then I stored all of these using a yi comma yi plus 1. Like let's say that we have stored 1 and 4, right? So it's our, like, we know that we'll be forming edges between 1 and 4. So obviously we'll be forming edge between 1 and 4, right? It's obvious, because it's there is no edge between them, that's why they are distinct. And when we connect this was my v1 vector of pair, and this was my v vector of pair which stored the cyclic ones. So we know that if we cut this cycle and we join this v1, that's that's our answer, right? And this output format is also something like that, IJUV, which means that road between cities IJ become closed and new roads within UV. So new roads will be obviously, sorry, new roads will be obviously 1 and 4, which were not connected, and this cycle will be cut. So that's the concept of this question, and that's it. I got an AC using this code. So that's it for you, disjoint set union. If you have any kind of doubt, try solving all of these questions. If you have any kind of doubt, ping me up in the comment section below. Like, share, and subscribe the channel. Thank you for watching this video. Stay tuned for more videos of graph theories.